Here we are again with the whirlwind part of the course. I want to remind you what we were doing. We did this in a big hurry flurry last time. We're going to extend it some more tonight. Anybody have any questions last time that you wanted to ask? You'll think of someone as I review. Vector in the plane is nothing more than a directed line segment in the plane. In other words, a vector from P to Q, point P to point Q here, it's just a line segment. Here's the line segment from P to Q. Together, the specification, which is the initial point, which is the terminal point of the two endpoints. So we write PQ, or we like to write something short. I'll just write V for vector, little arrow over the top. The book will use boldface. All right, that's hard to draw on the board, so I'll use the arrow notation, which is very common on chalkboards and whiteboards. So here's the vector from P to Q. Now it has an x displacement and a y displacement. We call the x displacement V1. It's the difference in the x coordinates. And the y displacement V2 is the difference in the y coordinates. If you say that P has coordinates x0, y0, and Q has coordinates x1 and y1. So I've defined the components of the vector V1, V2, and then we said two vectors with the same components anywhere in the plane will be called equivalent. So we write V equals V1, V2 in terms of its displacement. And then we said if we also introduce these additional vectors, I, which is a unit vector, you can put it here or you can put it up here. Let's put it up here this time. I, which is 1 unit long, and J, which is 1 unit long vertically. Then you can also write this in the notation V1 times I plus V2 times J, where you've introduced this vector addition and multiplication by a scalar. Sum of two vectors, you just add them component by component. This plus this, and this plus this gives you the components of a new vector. We said that had a parallelogram law. If you drew those at some point, such as the origin, sum of the two vectors reversed this parallelogram got by putting these end to end. In other words, if this is B and this is W, you take a copy of W and you put it over here. And this is B plus W in the middle. But vector addition is commutative. You can add in either order. So you can also take W followed by V put in the end. And vector addition defined this way gives you the vector that's the same as if you put these two at the end, take a copy of V, put it at the end of W, and then from the initial point of W to terminal point of V, that vector is also B plus W or W plus V. Multiplication of a vector by a number, you just multiply the vector times each component. And the dot product was defined this way. Right? Dot product of two vectors is actually a number, right? This times this plus this times this. That number, V1, W1 plus V2, W2. So then we also had the length of a vector V, which is the length of the line segment that it is. So you use the Pythagorean theorem here, and you said the length is just V1 squared plus V2 squared square root. This is also called the norm of the vector, so you'll see that terminology too. So this is length or norm, or magnitude, is another word, of a vector V. All right, so it's a lot of review. I'll do a fun example just for this. Suppose I had this kind of situation where I've got a weight hanging and maybe it's 100 pounds by two cables attached to the ceiling. And it's just hanging there in equilibrium. And so now, what is the tension in each cable? Tension is the force that's being pulled on each cable. Tension is a force. So if this is F1 and this is F2, two vectors for the force, and this is in gravity, find the strength, the length of F1 and the length of F2. How many pounds of force are in each of these cables trying to hold up a 100-pound weight, right? We can do that with this vector algebra, right? You can say, well, let's see. If suppose this angle is 30 degrees, this angle is 45 degrees, what do we know? We can break up these vectors into components. We can say this vector here, this is 45 degrees, this is also 45 degrees. And then there's a force vector for the weight. The weight is pulling down with 100 pounds. And it's exactly balanced by the sum of these two vectors. So this one What are these vectors here? We can break this vector up into its components knowing that this is a 45-degree angle, right? This side here, this component here, if it's at 45 degrees and its length is length of F2, this side will be length of F2 times the cosine of 45 degrees, all right? In any right triangle, this is the hypotenuse times the cosine, and this is the hypotenuse times the sine. So this over this is cosine, and this over this is sine. And then similarly, this one will be the length of F2 times the sine of 45 degrees. Okay. And now what do we know? This weight has no horizontal component. It's strictly vertical. So we know that these two components cancel for it to be in equilibrium. In order that it doesn't move sideways, those forces have to balance. We know that length of F2 times the cosine of 45 degrees, that's that one, be equal to, well, we can break this one up into components too, right? We can say it has a component which is negative. But the length of this side here is length of F1 times the cosine of this angle. Well, alternate interior angles, right? These are parallel, so these are both 30 degrees. And in this triangle, then, this one is length of the hypotenuse times cosine 30 degrees. Length of the hypotenuse on this one is length of F1. And so this one is length of F1 cosine 30 degrees. Those balance so that it doesn't move horizontally, right? But this component here exactly balances this component here. Now also the vertical components, these two, this one and this one together exactly balance the 100-pound weight down. So if I say this one is the length of F1 times the sine of 30 degrees, right? Opposite side to this 30-degree angle. And this component here is length of F2 times the sine of 45 degrees. Some more room, though that so these two vertical components, F1 sine 30 degrees plus F2 length sine of 45 degrees. Two upper ones have to exactly balance the weight going down so that it doesn't move vertically. That has to be equal to 100 pounds. There we go. Two equations for the block to hang in equilibrium. Well, now we've got it actually, because if you think about it, we can evaluate these trig functions quite easily, right? Rewrite these two equations. I'm going to subtract this over just to get 0 on the right. And I'll say minus f length of F1 times the cosine of 30 degrees. Maybe you remember cosine of 30 degrees is square root 3 over 2. I evaluated that and added over here. Plus this one, length of F2, times the cosine of 45 degrees is square root 2 over 2 equals 0. That's the first equation rewritten with the sine and cosine evaluated. Now the second one, I can just leave it in the order it's in. Sine of 30 degrees, right, is 1/2. So this is length of F1 times 1/2. Plus this one, length of F2, has to multiply the sine of 45 degrees. That's square root 2 over 2. And that has to add up to 100. Written in that way, I recognize that this is two linear equations and two unknowns. We can always solve a system of n linear equations and n unknowns, or so that it has no solution. That's a well-known area of mathematics. Now, how do I go about this? One way is to write these as two equation numbers. And there's two things you can do. You can solve for one of these things, length of F1 or length of F2, in terms of the other from one equation, maybe from this one, and substitute it into the other. That works. I'm going to use what we call elimination and add a multiple of one equation to another to eliminate one variable. I noticed if I just took equation 1 or equation 2 minus equation 1, these two would cancel, right? I take this one minus this one, I'd get no more F2 in there. So let's try that. Let's try to eliminate F2 by what we call the method of elimination. We write an equation that's equation 2 minus equation 1. So this one minus this one gives us 1/2 F1 minus a minus square root 3 over 2 F1 is a total of 1/2 plus square root 3 over 2 times the length of F1. I add this one, I take this one minus this one. Then I take this one minus this one, I get 0. And over here, then I take this one minus this one, and I get 100. Now I've reduced this to one unknown in the equation. All I have to do is divide through by this number, or multiply by its reciprocal. And I get that the length of F1 has to be 100 times the reciprocal of this. Well, if this is 1 plus square root 3 over 2, this reciprocal is 2 over 1 plus square root 3. There exactly is the force tension in string 1. What do we do for string 2? We now plug it into either equation. Let's plug it into 1. That looks easier. We plug it back into equation 1. We've got minus 100, minus 200. Let's write it out this way. Minus 200 over 1 plus square root 3. Not minus, plus 200. By the way, this isn't rationalized. If you can make this a little easier. By multiplying top and bottom by 1 minus square root 3, you can write this as 200 times 1 minus square root 3 over 1 plus square root 3, 1 minus square root 3 is minus 2. But if you rationalize the denominator by multiplying top and bottom by 1 minus square root 3, you get this. Which then comes out to be 200 or 100 times square root 3 minus 1. I'm doing a lot of fast algebra there. But the idea is you just reduce, this reduces to this. This is approximately 173 minus 1, approximately 73 pounds. This one, now we plug it into equation 1 and say minus this amount. 100 square root 3 minus 1. That's this times square root 3 over 2. Plus length of F2 that we don't know yet. Times square root 2 over 2 equals 0. So I just plug this number I got back into equation 1. And now I recognize, oh, I can just multiply this equation through by 2, and those would go away. So I can add this over to the other side and get length of F2 times square root 2 equals 100 square root 3 minus 1. Now divide by square root 2, and I've got length of F2, which is the pounds of force in second chord there, is 100 square root 3 minus 1 over square root 2. Maybe you prefer multiply top and bottom by square root 2 to rationalize this denominator. Then you've got 100 square root 6 minus square root 2 all over 2, or better yet, 50 times square root 6 minus square root 2 pounds. So there's the tension in the second string. Here's the tension in the first string. And we solved the problem. But you can see how these vectors are very nice. You have equilibrium problem like this. These two vectors have to exactly balance the vector that's coming down. Here's our force diagram. Force this way, force this way, force this way. Adding up to the 0 vector gives us these two equations that we can solve to find out how much tension is in each string. I think it's a fairly elaborate example of vectors. Questions on all that? Okay, well, we had last time also the projection of one vector onto another. We have yet to do a good problem on that. Projection of a vector v onto a vector u. Book likes to use v. I kind of don't like that way. I'll say it's u. Is what? It's the projection of v onto u equals v dot u over length of u squared times u. That was the definition. Well, we made that definition for a very important reason. That if you have a vector v, a vector u, this is precisely the vector you get by thinking of a light source at infinity, making a projection down onto this vector, like this. That's geometrically what the projection comes out to be when you make this definition. This also says something very useful when you're talking about these things like this vector diagram here. You like to break these vectors up into components. Here's a horizontal component. Here's a vertical component. What if I want to do that with this kind of a thing? the components aren't necessarily horizontal and vertical, maybe they're referenced like this to some body that's at an angle. What we now do is we also say, well, this vector here, sometimes called the vector component of V, orthogonal to U, is this one. This is V minus U. Because we remember the triangle diagram, if you have two vectors V and U, not U, V minus projection. Now, V and this vector, their difference is the vector that goes between their endpoints. That was another picture that we drew. And so you can break a vector up into vector and another perpendicular vector. Let's just try and compute a projection for now. Let's say, suppose I have V, the vector 4I plus 5j plus 3j, excuse me. Also denoted 4, 3. You can use either notation you want to call. Find the projection V onto U, where U is the vector on 1, splitting the two axes, X and Y. What is the projection of this vector onto the vector 1, 1? It's all just a matter of calculating this formula. Right? We'll say that this projection V onto U, V dot U, just like we said up here. I'll just use the formula. V 4, 3 dot U, which is 1, 1, over length of U squared is length of little thing on the side here. Square root of 1 squared plus 1 squared, right? The root sum square of these components. That's the length of U, but I want length of U squared. Oh, it's just the sum of the squares. Whenever you have a sum of two vectors, you have this important note. If you take the length of these squares for any vector, it's just first component squared plus the second component squared. Because the length is the square root of this, the square of the length is just the sum of the squares here. So this will be 2 on the bottom. So the projection is just this dot product over 2. Oops, I'm sorry. And then times U, times 1, 1. This number, V dot U over length of U squared times the vector 1, 1. And well, what have we got? Remember dot product, this times this plus this times this. It's 4 times 1 plus 3 times 1 all over 2. That number, multiplying the vector 1, 1. It's, let's see, 7 halves times 1, 1. Remember, when you multiply a vector, a number times a vector, it just multiplies each component. So it's the vector 7 halves, 7 halves. There's the projection. This vector with components 4, 3, onto the vector with components 1, 1. I'm going to draw the picture for this. Kind of neat. Now we got the same picture of it as before, but at an angle. Let's put these at the origin again because it's easier to work with vectors there. Then their endpoint is the same as their components. So I've got the vector 1, 2, 3, 4 by 1, 2, 3. This one right here. C. And I'm going to project it onto this close by vector with components 1, 1. But it's much shorter. There's U. What do I get from this projection? I get the vector that's obtained by extending this 1, 1 vector out through 4, 4 out here. And then dropping this perpendicular here on here, running right along U, is the projection of V onto U. That's this one, 7/2, 7/2. And you can kind of tell from this picture that what's left over here is going to be rather short, right? What is this going to be? This is going to be the orthogonal component, V minus projection of V onto U. Well, what is it? It'll be at a right angle to this one. So the projection of V onto U goes in the direction of U because you just project it, right? Thinking of the light shining it down onto this line here that contains U. V minus the projection then is the original vector, 4, 3. Subtract 3 halves, 7/2, 7/2. And you get the vector 1/2 minus 1/2. That's this one. Now we can write the V is the sum of these two vectors, one of which is parallel to U and one of which is perpendicular to U. As follows. 4, 3 is, in fact, 7/2, 7/2, a vector in the direction of 1, 1, but just 7/2 times long, plus this vector is perpendicular to it, 1/2 minus 1/2. So this is parallel to vector U. This one will be perpendicular to vector U. And you can do that with any two vectors, as long as the one you're projecting onto isn't the zero vector. You can break it up into a parallel and perpendicular component like that. Now, if you have a force diagram here with some rocket that's pointing at this angle, you can find the force that's in the direction of the rocket's motion and the force that's to the side of the rocket's motion trying to make it turn, right? So that's the kind of application you can get out of this projection. There's a lot of complicated stuff, but you can see it comes up with kind of neat results. Well, this brings up an important topic. How do you know when two vectors are perpendicular? Well, it's like this. Note, we had before, by theorem, that V dot W is equal to the length of V, length of W, times the cosine of the angle between them, right? That was our theorem for that made these dot products so useful. How do you know when these vectors are perpendicular? The dot product is a very easy way to find out. This is equal to 0. These are perpendicular only if the angle between them is 90 degrees. Theta equals 90 degrees, giving perpendicular vectors. As long as V and W aren't the zero vector, so that their length would be 0. The only way you can make the right-hand side equal to 0 is if cosine is if cosine. If theta is 90 degrees, then this is 0. Cosine of 90 degrees is 0. These can't be 0 if they're not the zero vector. So, the two vectors are perpendicular, if and only if B dot W equals 0. IFF means if and only if B dot W equals 0. This suggests we make an extended concept of perpendicularity. We're now going to say, therefore, make the following definition. We will say that B is orthogonal to W if and only if, or well, if, since it's a definition, meaning if and only if V dot W equals 0. Otherwise, they're not orthogonal. And this extends the idea of perpendicular vectors, right? Now you can, what this means is for non-zero vectors, they're called orthogonal if and only if they're perpendicular. And for zero vectors, what do? We couldn't talk about perpendicular before. Basically, we're saying now that orthogonality generalizes perpendicular. It's equivalent to perpendicular when you don't have zero vectors, but now the zero vector is effectively perpendicular to every vector in the sense that it's orthogonal. This generalizes perpendicular to include the zero vector. The zero vector will be perpendicular to every vector. Now you have an easy way to test whether vectors are perpendicular or not. This example is the vector 5 minus 15 perpendicular, say orthogonal, to the vector 3, 1. Well, it is because, right, we just take their dot product to check. 5 minus 15 dot 3, 1 equals, let's see, 5 times 3 plus minus 15 times 1. Sure enough, it's 0. So the answer is yes. The vectors will be orthogonal if and only if their dot product 0. That's the way it's defined. Then the zero vector dot anything is 0, so it's perpendicular to everything. Well, makes a very easy way to test when vectors are orthogonal. More than that, you have the following result. For V and W both not the zero vector with all components 0. The angle theta between them one is acute, meaning less than 90 degrees, if and only if V dot W is positive. How do we know that? It's again from this relationship. Because V dot W, let's put it on the side. Let me write the theorem and then I'll write the derivation here. So it's acute if and only if the dot product's positive. It's obtuse, meaning bigger than 90 degrees. And only if V dot W is negative. Or it's 90 degrees if and only if V dot W We already did the v dot w equals 0, that came out of this. But here's the reason or the proof. It simply comes out of v dot w is length of v, length of w, cosine of the angle between them, right? But for non-zero vectors, the length can't be 0, so this is positive, and this is positive. It follows that this will be positive if cosine is positive. This will be negative if cosine is negative. This will be 0 if cosine is 0. But cosine is positive for acute angles, right? Between 0 and 90. I mean, instead of saying acute, I need to include the 0 angle here. Let's write it this way: 0 less than or equal to theta less than 90 degrees. This one, 90 degrees is less than theta, is less than or equal to 180 degrees. So that's obtuse or 180 degrees. No angle. In that case. All right, so cosine theta is positive for a theta between 0 and 90, so that shows you'll get a positive number if and only if the angle's between 0 and 90. Cosine theta, we already talked about, is 0 for theta equal 90 degrees. And then cosine theta is less than 0 for theta between 90 degrees, 180 degrees, including 180 degrees. So that's the derivation. It's sine of the dot product just depends on the cosine of the angle between them. Therefore, you get this result. So it's easy to tell if the angle between two rays is acute or obtuse or 90 degrees. You just take the dot product, see whether it's positive or negative or 0. All right, now here's another thing too that we should be aware of. We got this additional theorem which we were mentioning last time. For any vector b and scalar c, that is number c, what do you think the length of c times b is? You can already see it. If you just try a simple example, you got a pretty good idea, right? For here's the vector, for instance, 2, 1. And what if I take the vector 3 times 2, 1? Then I get this long vector here. 3 times 2, 1 is 6, 2. And if you think about it, it's the same direction, but 3 times as long. If I take the vector minus 2 times 2, 1, we get the vector and multiply this into each of these components. Minus 2 times 2 is minus 4. Minus 2 times 1 is minus 2. And you get a vector that's twice as long in the opposite direction, but along the same line. So these vectors are all parallel. 3 times the vector, the positive multiple of the vector points the same direction, though, and 2 times the vector, minus 2 times the vector, a negative multiple points the opposite direction. All 3 parallel. What's the case in general? We can apply this theorem. This, in general, if you multiply a number times a vector, the new length is actually equal to c times the length of the original vector, absolute value here. So multiplying any vector by a number c, its absolute value c times as long. And let's do the proof of that one there. It's really easy, so it's worth doing. Length of CV is the length of the vector CV1, CV2 But what's the length of a vector? It's the root sum square of its components, right? It's square root of CV1 squared plus CV2 squared. And this is just an example down here. And so now you can factor C squared out of each of these. Say this is the square root of C squared times V1 squared plus V2 squared. But now this square root of the product is the product of the square root. Square root of C squared times square root of V1 squared plus V2 squared. But square root of C1 squared is absolute value of C. And square root of C squared is absolute value of C. And this is the length of V. There's the proof. It's as short and easy as that. Whenever you multiply a vector by a number C, it becomes absolute value C times as long. Then also we will say a vector is parallel to another if it's just a multiple of the other. So this vector is parallel to this one because it's a multiple, and this one is parallel because it's a multiple. So we observe from that that these vectors are all parallel. And we'll say if C is negative, we say they're opposite direction. If C is positive, they're the same direction. And then definition, let's write it down. Vectors V and W are parallel if one is a multiple of the other. I say one, normally they're both multiples of each other, but in case one of them is a zero vector, it's 0 times the other. You can't get the other one back by multiplying zero vector. So let's say at least one is a multiple of the other. Multiple C of the other. And then if C is greater than 0, they have the same direction. Say, or if C is less than 0, they are opposite direction. There's some nice theorems in there. And then one more note. What about these unit vectors? Recall a unit vector is a vector of length 1. Any unit vector U has the form U equals cosine theta, sine theta, or some theta. In fact, it's theta equals the angle in standard position along this vector. How do we know that? I introduced this because this really gives you some nice intuition for these, and sometimes it's hard to pick this out of the textbook. But suppose I have a unit vector in any direction. Maybe this is it. 1 unit long, right? This is my vector U. What do I know immediately from trigonometry? I know the terminal point is on the unit circle, right? The unit circle is all points at distance 1 from the origin. But also from trigonometry, what do we define this point here? If the vector is at an angle theta and 1 unit out, what do we define it to be the coordinates of the point? We say cosine theta is defined to be the x coordinate and sine theta is the y coordinate. It follows just from this trigonometry definition that any unit vector, since its terminal point is on the unit circle, has components cosine theta, sine theta, where theta is the angle in standard position. This means you can construct a unit vector at any angle you want just by writing cosine theta, sine theta. That's a real convenient thing sometimes. Those things really help your intuition a lot, I think. And then, we want to talk about some more applications of the dot product. One of the most important applications is work in the physical sciences. Another definition. In Calculus 4, you get to see how useful work is. We really can't get into the deep theorems this semester on how to use them, but we'll introduce the concept of work. If a force vector F that's constant moves an object treat it as a point object. All right, so it's like you pick some point on it and say, this is the position of the object, and you just follow that position of the object. By some displacement vector from its initial position, d. So d for displacement. Then the work done, finding work, by the force F on the object is W work equals F dot D. So the dot product also defines work. Look at all those great things we got. We got the dot product we saw last time determines the angle between two, tells you the angle between two vectors. We saw also that it tells you the projection of one vector onto another. And now it's also going to do work here for us. And this is the idea. I have some object here and it's moving along a path and goes through a displacement D under the influence of some force F, not necessarily in the same direction. Like maybe gravity is actually holding the object down and it just kind of slides along the ground here without friction. Then what is F dot D? This is geometrically showing what you have. I'm going to say that you may have heard before that work is force times distance. Have you ever heard that before? Provided the force is pushing in the same direction, force times distance along a line. If the force points along the line and you make a displacement vector d, then it's just the length of force times the length of the distance. But if the force is in an angle, what you're really doing here is you're considering an angle theta between them, and you say F dot D, since it's length of F, length of D, cosine of the angle between them, it's not the work done by force at an angle to an object is no longer force times distance like you had when everything was moving along a line. Then you had the force pushing along the line and the displacement push along the line. When force is not along a straight line but can be at an angle to it, then you generalize it and say it's not force times distance, it's force times distance times the cosine of the angle between them. There it is. So that's what this is. In other words, it's the since this is actually a triangle here, length of F times the cosine of theta, the work is the force along the path times the displacement. That makes this a special case of this, right? Instead of force times distance being work, when you're just dealing along a line, if you have a force that's at an angle here, then the actual work is the component of the force in the direction of P, the projection, multiplied by the distance. That's what work is. Projection of the force out of the same direction times distance. So geometrically, it's nice to know what it is. It's this component of force times the distance. So we can do an example of that. This is my favorite example of work. Suppose a child pulls a wagon. Let's say a 10-pound wagon. Force is pounds is actually a unit of force. It's not a unit of mass. Kilograms is mass, but if you have to multiply kilograms times the acceleration of gravity, right? Mass times acceleration gives you the force in newtons. So if you get a force in the metric system, it's in newtons. If you get a force in the English units, it's pounds. And the mass is in slugs, and you take slugs times acceleration of gravity, then you get pounds. So this will be a force on the wagon. The child pulls a 10-pound wagon, pulls a wagon, sorry, a wagon with 10 pounds of force. Child applies at a 30-degree angle to the path that the wagon is pulled along for, let's say, 20 feet. How much work does the child do? How about that one? I like to draw the picture on this. It's a lot like the last one. You pick some point on the wagon, you say, that's where the wagon is. Maybe it's the center of mass or something. And the child pulls like this with a force vector that's 10 pounds at an angle of 30 degrees from horizontal. And the child pulls this thing 20 feet. Point A to point B, 0 to 20 or something. How much work is done? You would like to say the force is 10 pounds times 20 feet, 200 foot-pounds, but it's not, right? The force is actually the component in this direction. We'll say the work times the distance places. So work is actually force dot distance, displacement, excuse me, force dot displacement. What's the force? The force here, I can break it up into components. If this is 30 degrees, then the y component is 10 times sine 30 degrees. And the x component is 10 times cosine 30 degrees, just by trigonometry, right? Then this over this is cosine, this over this is sine. Those are the components. So the force is actually, and the sine of 30 degrees then is a half. So this is 10 times a half, it's 5 pounds. And over here, cosine 30 degrees is square root of 3 over 2. So this is 10 times square root of 3 over 2, is 5 square root of 3. So the force vector is 5 square root of 3 in the x direction, 5 pounds in the y direction. And we're going to dot that with the displacement vector, which is just 20 horizontally. It's 20, 0. What do we get? 5 square root of 3 times 20 is 100 square root of 3. Let's write it out. How about 5 square root of 3 times 20, this times this, plus this times this, 5 times 0. Evidently, that comes out to be 100 square root of 3 foot-pounds. The units of work are force times displacement, right? Just coming out of the line example. So it's foot-pounds is the English units here. Sometimes people put LBS for pounds. We'll just use LB. There it is. It's about 173 foot-pounds. If you want to know actual measure. F. So there's an application to work. How about that? I could comment that there's another way to do this. Instead of actually taking the dot product, you can say that work equals force dot displacement is the length of the force vector, the length of the displacement vector, times the cosine, the angle between them. This is convenient because we know the angle between them. It's 30 degrees. So the length of the force vector, since it's 100 pounds, we know is already 10 pounds. We know is 10. That's this one. The displacement is 20 feet, and then we just have cosine of 30 degrees, and we got again 200 cosine of 30 degrees is square root 3 over 2 is 100 square root 3, just like we got before. You can also do it from this theorem here. Either way is just fine. I like this because it illustrates the dot product. I like this because it illustrates when you have the angle, you can figure the work without doing this. So there's a problem on the homework that I'd like you to be aware of. This is the kind of thing that they'll do in your physics class. Common problem. How much work is required, ignoring friction, to push a 100-pound child up a 30-degree ramp? This is very similar to the example we just did. Excellent. I really think it behooves you to draw the picture, right? So here's a ramp being 30 degrees from horizontal is what I mean. And the child weighs 100 pounds. And if you put them on something relatively frictionless, like maybe a sled, here's a sled and a child sitting on top of it. And I neglected to put how far this is. For 10 feet. What do we have to do? Well, force of gravity on the child looks like this. Force of gravity. And you can break gravity into components. You can break it into a component this way. And this way. And now, if this is a 30-degree ramp, then by similar triangles, this is also 30 degrees. The force of gravity is 100 pounds, right? Pounds is a force. And so what is the component of force that's pushing the child downward? This component here is 100 sine 30 degrees or 50 pounds. In other words, you have to overcome gravity to just overcome gravity. You have to push the child with 50 pounds of force to push the child up the ramp. Now, I'm going to push for 10 feet. So the work is going to be the force times the displacement, since it's along the same line, is going to be 50 pounds of force to overcome this component of gravity times 10 feet I have to push is 500 foot-pounds. 50 pounds times 10 feet, 500 foot-pounds. Book also brings up an interesting thing. You can say that this is the work done by you. It's also the work done against gravity. So the work done against gravity, and then gravity pushes with 500. Yep. With the same force the other way, 50 pounds at the same time. All right, so there's work pushing something up a ramp. I think that's pretty much all I need to say on there. Try the problems. I gave you quite a few of these on here because as you can see, there's quite a few concepts. Now we need to do 3 dimensions. This is all vectors in a plane. Nice thing is it's completely analogous. It's really nice. Similarly, in 3 space, a vector is a directed line segment in 3 space. It's just harder to draw, right? So if I draw a vector out here coming out of it, it has an x component, v1, y component, v2, and a z component, v3, right? You go this far in the x direction, and then this far in the y direction, and then this far in the z direction. And we say vector v here has 3 components, v1, v2, and v3. Like that. And this is how you can draw a vector, right? Just like we started drawing in section 11.1, you can draw the rectangular box. With these sides, v1, v2, and v3. And then the vector will go from the origin, if it's a vector at the origin, out to the corner of the box. That's how to draw these things accurately. And then now once again, you do make the same kind of definitions. We'll say also similarly, addition is component by component. So for instance, 3, 1, 2, plus, minus 1, 2, 0. You just add component by component, 3 plus minus 1, 1 plus 2, 2 plus 0, gives us 2, 3, 2. You just add vectors component by component. If you take a number times a vector, 2 times a vector 1, 0, minus 4, you multiply all 3 components down, you get the vector 2, 0, minus 8. And now how should we extend the dot product? The dot product extends completely naturally too. And if you take V1, V2, V3, dot W1, W2, W3, once again, the dot product of 2 vectors is a number, and that number is now just got by taking this times this plus this times this plus this times this. V1, W1 plus V2, W2 plus V3, W3. And furthermore, the theorem carries over. It doesn't matter that it's in 3 space, you can still show that the dot product of V with W in 3 space is once again length of V, length of W, cosine of the angle between them. This is significant because the angle in the plane wasn't so hard to find. Dot product was convenient, but you could do it without too much work. Try finding an angle between 2 line segments that intersect in three-dimensional space. It's pretty tough, actually. And so, this is a nice way to find the angle between two vectors. It's the same as before. It's just the arc cosine. If you solve this for theta, you get theta is the arc cosine of b dot w over length of b, length of w. And once again, you don't have to worry about what quadrant. The arc cosine is always between 0 and 180 degrees. And so this gives you just the angle you want between the two vectors in three space. So all these theorems carry over nicely, and you can do exactly the same things. You can compute work by taking the dot product, for instance. All that stuff is just the same as it was before. There is one additional concept, however, now that you're in three space. We're going to introduce the direction angles. Alpha, beta, and gamma will be the angles between the vector and the three positive axes. And we'll say vectors in the direction of the axes are I, the unit vector in the x direction, right? It's 1 unit long because you can root sum square its components and see it's 1 unit long. Now it'll have three components moving along the x-axis. Vector j in three space will be the vector 0, 1, 0, moving along the y-axis 1 unit in three-dimensional space. And we'll add k to that, which is 0, 0, 1 unit along the z-axis in three-dimensional space. The direction angle between a vector v and these three unit vectors moving along the axes, these are, what are they? Turns out they're very easy to find these angles between the axes in any vector. And sometimes that's useful, right? If you're in construction or something, you want to know what angle to turn things at. Here's the picture. I take a vector v, right? It has some angle alpha down on the x-axis, some angle beta to the y-axis, and some angle gamma to the z-axis. Once in a while, you need to find those, and you think maybe those are pretty complicated to find, right? Not so. They're pretty easy. The direction angles, in fact, are, let's say, satisfy, and then you can take the arc cosine to find them. It's easier just to remember the cosine. The cosine of alpha is just the first component of b over its length. The cosine of the second angle beta is just the second component over its length. And the cosine of the angle to the z-axis, gamma, is just b3 over the length. And then use the arc cosine to find these. Right. So, for example, suppose I took the vector v equals 1, 2, 1. Right? Find the direction cosines for this vector. What angle does it make with the three axes, right? So these are the direction cosines. And these are the and alpha, beta, gamma are the direction angles. Let's just say find the direction cosine from which you could take the arc cosine. Well, cosine alpha is so easy, right? You just take the first component, 1, divided by the length of the vector. We simply need the length of the vector is root sum square root square root of 1 squared plus 2 squared plus 1 squared is square root of 6. So the first direction cosine is 1 over square root of 6. Take arc cosine of that, you got the angle of the x-axis. cosine of beta is 2 over square root 6. Huh? And the cosine of gamma is 1 over square root 6. There we are. We can find the angles for the three axes. So there's this little bit more you can do in 3 dimensions. But it's also really useful because things like finding the angle between two vectors or finding angles to the axes is much harder in 3 dimensions. This does it nicely without having to very convenient. So the next thing I was going to do is the next section on cross product, but I'm not going to get very far. I'm going to have to repeat it. So I'm thinking maybe I shouldn't get started on that tonight. Trying to think if there's anything else I need to do. Let's just do a couple of review examples, unless I start a new section and then have to repeat myself next time. Here's a couple examples that I like to do sometimes. These will just deal with general topics over what we've been doing. Find a unit vector in direction opposite to the vector v equals 4, 1, 3. What's a unit vector in the opposite direction? Well, we can make a unit vector in the same direction. How do we do that? We mentioned it last time, didn't get enough good examples, is why I picked this one. Unit vector, same direction. All you have to do is divide it by its length, right? Because if you multiply this by a number, or divide it by a number is multiplying by a reciprocal, multiply this by the reciprocal of the length, you'll get a vector in the same direction, right? Because that's what it means. Same directions if they're a positive multiple of each other. So unit vector, same direction. And then the length will be scaled by this, right? Is u equals v divided by its length, right? The length of the result will be the length of v times this number 1 over length of v, and it'll be 1. All right, so that's how you always compute a unit vector in the same direction, is divide the vector by its length. So I have 4, 1, 3 over the square root of the sum of the squares of those. 4 squared plus 1 squared plus 3 squared. Well, this is 26 on the bottom. So the vector here is multiplied by the number 1 over square root 26. And I get 4 over square root 26, 1 over square root 26, 3 over square root 26. We can simplify that slightly. I haven't rationalized the denominator. But there's a unit vector in the same direction. So what's a unit vector in the opposite direction? Just multiply by -1. So we want not this vector, but minus u. Mine is -4 over square root 26, -1 over square root 26, -3 over square root 26. Gives you a unit vector in the opposite direction. So sometimes you'll see these kind of things. And boy, it looks like I'm just about out of time there. I guess that's my last example then. I hope this was interesting. Bring me some questions next time. I think you'll find you'll learn more if you bring me some questions so I know it's hard. Here's the homework. Oh, I left it over here. I think I gave you some of this last time. 11.2, you want to look at 3, 9, 13, 23, 25, 27, 31, 35, 39, 43, and I said last time, these are pretty easy problems, so there's a lot of them. And 11.3 is on the dot product. This is on vectors, this is on dot product of vectors. I'd like to do 1 to 9 all of those. 15, 23, 25, and 27. This includes some word problem at the end, I think. So, thank you for coming in tonight. See you again Monday.